All right, everybody. So, as you can see from my title, I originally was going to call this a short review of limits. And then I realized I think it's more like a very short review of limits. Um, it's hard to decide. Like, if I had to just spend 15 minutes talking about limits or even 30 minutes talking about limits, what would I talk about so that it's not too simple, but it's not too difficult, and it's the right amount of detail that somebody could get something out of it. Like, for example, here's an old calculus book of mine, and this has like 75 pages of it just devoted to limits, and that's all very dense reading in that book, too. It's not easy to read that book and get something out of it. So, my point is, limits is a big topic. But I thought still I could tell you some things, and maybe I could make it general enough that you could find your own way, okay, if that makes sense. So maybe like I don't know, if I can like teach you how to learn rather than just teach you, that would be better. All right. So I'm thinking like here I'm more trying to teach you how to learn, maybe even on your own in the future as you go on and do whatever it is you do, rather than just tell you, here's the bare amount you need to know. I hope that makes sense. Anyway, so let's start with my first part. I wanted to establish these two limits as a jumping off point for some other problems I wanted to show you. Can we agree on each of these? As x goes to infinity or negative infinity, 1 over x goes to 0. And you can make a table to illustrate that. When people first learn limits in Calculus 1, sometimes tables are used to illustrate what's happening. And I can show you the table, and sure, the bigger the x is, the smaller and closer to 0 the y is going to be in either case. But I guess I like to think about this in terms of arithmetic. Like, I remember learning arithmetic in elementary school and then having the epiphany that the bigger number I divide by, the smaller my answer is. Okay? And that's all that this says. It says the bigger number you divide by, the smaller and closer to 0 your answer is. Okay? Now let's generalize this idea of arithmetic, that the bigger number you divide by, the smaller and closer to 0 your answer is. We can generalize it like this, that any constant divided by something down there, whatever that is, in whatever the problem is you're doing, that this part goes, I put goes in quotes because that's like real mathematicians don't say goes to infinity, but I'll put this in a way that ordinary people can understand it, but this part goes to infinity or negative infinity. That will be 0, okay? So there's like a general notion that you could apply. So can you see about both of these? Like in both of these cases, if x goes to infinity, then this part down there, whether it's e to the x power or x squared plus 1, they will on their own go to infinity. And that's why both of these limits are 0. I'll talk about e to the x specifically later, but these are examples of this general principle, which I think all begins with these two very basic problems. Okay. All right, so let's talk about different kinds of functions now. Let's talk about logarithms. Here's one way. Okay, so we can start learning limits by tables. Tables are probably the most obvious way to see it, but tables are not definitive. They don't always show you what you need to see. And here's the reason. Somebody could say, well, why did you stop at 10,000? And my answer would be, I stopped at 10,000 because I felt like I saw what I needed to see. But you never know. I mean, how much room is there between 10,000 and infinity? There's a lot of room there. I could have gone way further, okay? So here, I want to show you that sometimes we learn the shape of a curve in order to learn the trends between the variables, okay? So here's the curve of y is equal to natural log of x. So when you took algebra and pre-calculus, or when you took just about any math leading up to calculus, you learned the shapes of graphs. And one reason is that if I know the shape of a graph, then I can, like in maybe some other scenario, make some predictions about cause and effect between all the variables involved, all right? So it turns out that the nature of the natural logarithm curve is that it has this vertical asymptote on the y-axis, and actually the logarithm goes to negative infinity if the x goes to 0 from the right. Now on the other side, this logarithm curve, natural log of x, rises very slowly, but it rises forever. So there's no ceiling. You can say, like, at some point is this curve going to get above the pencil? And say, it will. It will take a while, but it will get above the pencil. And I say, well, okay, what if I put it up there? At some curve, at some point, will this curve get above that pencil? Yes, it will. At some point. It may take a while because it rises so slowly, but it will get above that pencil. Well, no matter where you put the pencil, it will get above it, all right? So here's what we can say. The limit as x goes to infinity of natural log of x is infinity, okay? So that's a general concept, all right? I can't illustrate this very well with a table, though. The reason is the curve rises so slowly, it's hard to see in the table. Like, you know, I might have to put some really, really big numbers in there before you really saw the pattern that I was trying to illustrate. That's why the tables are not definitive, and they're not all you need to know about limits. Okay, so I think I've made my point that, yeah, no matter how high up I put that pencil, this curve will at some point rise above it. All right, then that's the basis for this limit, knowing that property about the curve. Now we can generalize that. So you have the natural log of something, and then whatever the problem is you're doing, the part in here goes to infinity, okay? Now it's, again, like for me to write goes, like I probably shouldn't do that, but you know what I mean when I write that down, okay? So like here's two examples. Like you say x goes to infinity. Will x squared plus 1 go to infinity? It will. And so, you know, the logarithm of that will go to infinity. Because it's just like this, it's just like this, and it's this general principle. And take this one, x minus 4. It doesn't matter. X goes to infinity, so will x minus 4. That part in there is going to infinity. And I have the logarithm of that. So, all right, by this general principle, we're justified in saying that limit is infinity. Okay? All right, now that's if this part in here goes to infinity. It might be that, for example, like here, I'll leave you one to think about. How about this? Limit x goes to infinity, natural log 1 over x. Does this fit that general principle? Say x goes to infinity. Is this part in here going to infinity? No, not this time. Not this time. We talked about that one just a minute ago. If x goes to infinity, 1 over x will go to 0 from above. It will very gradually get closer and closer to 0. So, all right, turns out this one is negative infinity. Okay, all right. Why is that? Well, one, I wanted to show you that not everything that has logarithm in it is going to fit this general principle. This one doesn't. But say that part's going to 0 from the right. So it's like it's following our curve this way. So when you have the logarithm of a number, and that number in there is very gradually getting closer to 0, you're tracking your points like this on the logarithm curve. That means the y-coordinates are going down here. Follow them down there. Where are they going? They're going to negative infinity because here we have a vertical asymptote on the y-axis. Okay? But, you know, I could do any of these just by understanding the basic shape of the curve. Okay? So when we do limits, it's nice to understand a table can sometimes be useful. But at other times we need to be familiar with basic functions and their graphs, okay? All right, well, speaking of that, let's do an exponential, okay? So y is equal to e to the x power. E is about 2.718. It's an actual number there, okay? This curve, unlike the natural logarithm curve, it rises extremely steeply. It's very steep. Maybe you've heard of exponential growth, especially in our recent times. I'm sure you've heard of exponential growth. Very steep. It's not so steep here, but at one point it really takes off. Anyway, and I think it's obvious that if the x goes to infinity, if the x goes this way, the y is definitely going that way. The y is going to go to infinity. E to the x will go to infinity. This one's real easy to illustrate with a table. I mean, 2.7, 22,485 million. I'm only up to 20 for the x, and already my y is 485 million. 30, well, let me just say, that number's big, okay? So that curve rises real fast. It's real obvious that that limit's infinity. So let's generalize from this, okay? If you have in your problem, whatever the situation is, e raised to some power, and that power, by whatever's happening in the problem, goes to infinity, okay? Just like here, I'm saying the x goes to infinity, then e to the x goes to infinity, then e to that power is going to go to infinity. So that'd be true for this one, and it'd be true for this one also, okay? So you have a constant there times that. Well, that's not going to change it. Say I had like a constant here times this. Well, see, these numbers are going to get big, even if you multiply them all by something, okay? All right, so each of these is going to be under that principle. You might say, well, that's a 2. That's not e, that's different. Well, 2 to the x, that exponential curve is hardly at all distinguishable from this one, okay? As long as, this number is bigger than 1, you'll get an exponential curve that has the same property here and could fit into the same general principle, okay? And so you're curious about that one. Now, I did say that tables can be useful. I mean, they're not definitive. They're not the only way to go. You can't have all of your thinking about limits be based on tables, but they are still a useful tool. So here I showed the table for this one, natural log 2 times 2 to the x power. Yeah, and it's like other exponential curves. It gets very big very fast. Indeed, if x goes to infinity, natural log of 2 times 2 to the x will also go to the infinity. Okay, let's look at one more. I could easily make 4 hours of videos on limits, but what about inverse trig? Okay, now this one, there might be too much stuff here I want to show you, but I'm willing to take that risk. So let's talk about this limit. Say the limit as x goes to infinity of tangent inverse of x. Okay, so at first I wanted to show you a table. Like I said, that could be a useful tool. What's it looks like if x goes to infinity? It could look something like this: 1, 10, 100,000, 10,000. X going to infinity looks something like that. And I did some calculations, tangent inverse of the x. I put my calculator in degrees when I did this. 45 degrees, 84 degrees, 89.4 degrees, 89.94 degrees. Do you see a pattern? 89.99 degrees. I'm really starting to think I'm going to run into 90 degrees at this point. And sure enough, it's true. If x goes to infinity, tangent inverse of x goes to 90 degrees, or for when we're doing calculus, better to say pi over 2 radians. Okay? Now, that's fairly superficial. It's a table. There's not normally anything very complicated about a table. I want to get you to try to think a little bit deeper about this one. Okay? So think about what inverse tangent and tangent are. So they're just they're inverses of each other. All right, like square versus square root, or addition versus subtraction. In other words, you take tangent of an angle and you get a number. So therefore, you take tangent inverse of a number and you get an angle. Okay. All right. So if you took tangent of 45 degrees, you'd get 1. If you took tangent inverse of 1, you'd get 45 degrees. Now, so I wanted to find another way to see this limit. It's a little more sophisticated than the table. now remember, one thing I mentioned a little while ago is if you know the shapes of curves, that can help you see patterns among variables, all right? So I decided to draw the tangent curve here because I thought more people would be familiar with it than the tangent inverse curve. It does look like, so let's see, what's x? That's an angle, okay? And what's y? Y is a number, right? Because you take tangent of an angle and you get a number. Now, the tangent curve has a vertical asymptote at pi over 2. What happens if you follow the points like this on the curve? Then as the angle gets closer to pi over 2 or 90 degrees, the number goes to infinity. Don't you see that that's the basis for this? Okay, so as the number goes to infinity, the angle goes to pi over 2 or 90 degrees. We can see that on the curve. All right, now that's still not the only way to see it. I can see it on the curve, but let's go back to when you first learn what tangent is. So when you learn about tangent, you say, well, here's how you calculate tangent. You draw a triangle, and this is actually an issue of measurement, okay? You measure the sides of the triangle, okay? And you divide this side over that side. So that's really what it is. It's measurement and division. Now, I want to claim to you that if this triangle morphs in a way that that angle right there goes to 90, since tangent is y over x, that'll go to infinity. And the reason is think about it. Say I push that angle to 90, then the triangle will look like this, to this, to this, to this. That's what it's going to look like if I push this angle to 90. That triangle you see here connecting these sides is going to get taller. It's going to look more like that. The x side is going to go away. It's going to shrink to 0, in other words. So y over x is going to go to infinity. Isn't it true that the smaller number you divide by, the bigger answer you get? So yeah, I can see it that if the angle goes to 90, the number is going to go to infinity, okay? So that's another way you could see this one. It's more sophisticated to look at this way, but I think you should challenge yourself to understand things in the deepest way that you can.